How long will it take for 10% of a 1,000 gram sample of uranium-235 to decay? Now, according to your textbook, the half-life of uranium-235 is 703,800,000 years. Now, what that means, just to review, is it takes this long for half of the particular substance to go away. So, we use that information to calculate the rate of decay. So let's do that before we do anything else. We know that it takes this long for half of it to go away. Well, let's say at the beginning, let's pretend that at the beginning of time there was only 1 gram. So after 703,800,000 years, wouldn't there only be half a gram left? So we could use that information to find our rate of decay. So we're going to be using the formula A of t is equal to A sub 0 e to the RT. Remember, this is the final amount or the amount present at time t. This is the original amount, your rate of decay, and the time. So that's what all of the little pieces mean. So using this information, we have a half a gram will be left after so much time has passed. The original amount was 1 gram. E to the R, we don't know, but T is that number. Okay, now we need to solve this for R, because before we can answer this question, we have to know what R is. So we have 0.5 equals E to this number, R. To solve this equation, we need to take the natural log of both sides. When you take the natural log, you can bring the exponent down. And do you remember what the natural log of E is? Natural log of E is just 1. So from here we can divide both sides by this big number. So we have R as approximately equal to, I don't know if I can squeeze all this on my screen. There we go. Natural log of 0.5 divided by 703,800,000. So we have this number. This is negative 9.85 times 10 to the negative 10. So I just wrote it down so that I know what it is, but in my calculator, I'm going to store that in X. That way I'm not rounding anything until I get to the end. I'm just going to make a little note that I stored that in X. Now we know what our R is. Our R is that very special X that we just stored in our calculator. So, how do we answer the question? The question was, how long, that means we're looking for time, how long will it take for 10% of this sample to decay? Well, if we want 10% to decay, doesn't that mean that 90% is still there? Let me write that down. If 10% is decaying, that means it goes away. This means 90% is still present. That is a very important thing to know, because this is the amount present at time t. Okay, so we need to know the amount present. So if 10% is going to decay, 90% is still there. So 90% of 1,000 is going to be 900 grams. That's how much is still present. So let's put all of this into our formula. Remember, we're using this formula. So we have 90% of 1,000 is 900. The original amount was 1,000. E to the r, but our r is that special x that we stored in our calculator, times t. Remember, x is just a number. We have it in our calculator. So we're trying to solve for t. To do that, we need to divide both sides by 1,000. So that's 1. 900 over 1,000 will reduce to 9/10. Now we need to solve this, and to solve, we can take the natural log of both sides. So we'll have the natural log of 9/10 is equal to, you can use your power rule now, so we'll have xt natural log of e. And remember, natural log of e is just 1. So we need to solve for t. That means we divide both sides by that x that's in our calculator. So t will be approximately what then? So we have natural log of 9/10 divided by x. And we get this really big number. Let's see if I can write all that down. 106,979,777.2. So what does that mean? Time is equal to 106,979,777.2 what? Years. Let's go back and look at the original problem. Actually, this little thing that I wrote under the original problem. It takes this long for half of it to decay. That's a long time, right? Really close to 1 billion years for half of it to decay. So for 90% of it to still be there, or for 10% to decay, it makes sense that it takes 107 million years, right? By the way, according to your textbook, uranium-235 is used for atomic power. Cool fact number 1.